oxide, metal oxides. So I welcome, sir,
So thank you, sir.
and thank you for accepting our invitation
Yes,
for 2 times because at the time of organizing any FDP, the resource persons are very important, and
yeah,
thanks for your cooperation.
yes,
So already I have introduced you in the first day,
yes.
but
No
as
need.
a part of protocol,
No need, sir. Actually,
yeah,
let's start.
as a
Let's.
part of protocol because some members may be
Okay.
new. Yeah, I will take this opportunity. So Dr.
Sure.
Dattakumar Suresh Mhamane works as a faculty in the Department of Chemistry at Sangameshwar College, Solapur, Maharashtra. He obtained his PhD from National Chemical Laboratory, Pune in 2014. He worked on graphene synthesis for energy storage applications. He did his postdoc research from 2014 to 2016 at Yonsei University, South Korea, Seoul. He also worked at Nanyang Technological University, Singapore in 2011. Till date, he has more than 35 high impact publications to his credit. Few more papers and review are in pipeline. His total citation crossed 1500 and achieved H index of 18. He has been selected as a young associate of Maharashtra Academy of Sciences in December 2023. This prestigious award is given for outstanding research scientists in science and technology. In chemical science, only 8 awards are declared, and he is one of them. Very special thing, sir. Congratulations.
Thank
In his career span of last 15 years, Dr. Mhamane has performed research in the field of material science, covering both novel synthesis of oxides and carbon-based materials and their energy-related applications. Over the years, he has worked in many areas related to energy and environment, more specifically development of carbon and oxide-based electrodes for supercapacitors and lithium-ion batteries. So it will be honored to be you here, and with this introduction, I welcome you once again and request you to start your session, sir.
Okay. Thank you, sir. Thank you, Dr. Avinash Patil, sir, and his team for the nice and uh, good introduction. Yeah, that is okay that I have received award and so many things. That is not important, but as it is a part of yeah protocol, he has introduced me. That is fine. But yeah, the most important thing is that am I audible, sir? My voice is clear.
Yes, you're audible, clear.
So last time we discussed about nanotechnology. It was general coverage, and I spoke about the many things related to nanotechnology. And the the topic name was like nanotechnology and research opportunities. So it was so general talk, but today I'll be more specific and giving the talk on oxides and carbon-based functional nanomaterials. So what is the meaning of this is if you talk about oxides, semiconducting materials are there, and if you talk about carbon-based nanomaterials, there are many applications again in for these two kind of people or these two kind of functional materials or nanomaterials we can say. But again here, in order to avoid the generalness, I will be more specific upon more specifically talk on the energy storage sector, how it is so simple to play with oxides, to synthesize oxides and carbon based nanomaterials, and how uh, people, students, research students can get paper, what we need to think, what are the general ideas about the synthesis, and what kind of things are required for paper publications. So these things I will be more focusing in today's lecture. So talk of my the title of my today's talk is oxides and carbon based functional nanomaterials. So this is the outline for today's talk, that I'll be speaking more specifically on energy storage, although there are many applications of oxide-based materials and carbon-based nanomaterials. But I'll be specific today on energy storage applications. Then I will briefly introduce or highlight some of the points related to key points related to supercapacitor and lithium ion battery. Then in between slides, I will go with carbon based nanomaterials. What kind of opportunities and challenges are there that people want to work in carbon based nanomaterials, and how can we start research, like those things I'll be covering in today's talk. More specifically, what I did during or what I am doing with carbon and oxide based nanomaterials, that I'll be speaking today. So next slide, I'm again coming to the energy. Last time we discussed that, but not in the context of the energy storage. So I'll be shifting my lecture from nanotechnology to now in the field of energy storage. So if somebody asks me why energy storage is a big issue, so after the question mark, definitely we can say that there are n number of opportunities. There are a number of opportunities. So I hope you are I'm trying to give a message that if there is a question, it means that it is a challenge. And if it is a challenge, there must be a number of opportunities to solve that particular issue. So why energy storage is so important? So as far as energy is considered, it is similar to a coin. Like a coin has two sides. Similar to that, energy has two sides. The first is a generation of energy, and second is a storage of energy, or energy storage, we can say. So generation, I already discussed. We have to balance the system, that we are not go. I mean, there may be depletion after a few years, many years, but we have to go. We have to go with the renewable sources like solar cell and wind energy. So what is the problem? The problem is incoherence between the generation and its uses. Generation of energy and its uses, we can say. So what does it mean? For example, sun is not available during the night time. That is a problem. So what people can do? People can produce energy in the daytime, and the produced energy we have to store somewhere. So where to store the energy? And that is the thing that I call it as opportunity. So generated energy can be stored by means of many devices, but the things that I am working is capacitor and batteries. Okay, so that is why there are many faces. You can see the faces. I mean, the emoji, they have question on their face, but the uh, yellow color one is a energy storage device, which is efficient device, which is a robust device, and which is good energy storage device, we can efficient energy storage device, we can say. So whatever the incoherence between the energy generation is there, okay, and the non-availability of the sun is there, but we can store that particular energy in the form of some devices known as energy storage devices. So energy storage devices is a big, no, it is not a big issue. I think it is a big opportunity for researchers to work. Okay, so what kind of thing is there as far as energy storage comparison or energy storage devices are considered? So what is the meaning of energy storage? The charges are going to store in the devices. Okay, like our mobile, we are charging, okay, in the night time, and then during the daytime through the applications we are going to discharge that particular battery. So because of that, I mean, this is a kind of advantage of energy storage device. So what are the different types of energy storage devices, and what kind of energy and powers? So energy and powers are the parameters for the energy storage devices, we can say. So this is a Regone plot, and this is I mean, a student or any person or researcher, we can say, has to understand what kind of things that energy storage devices can deliver in terms of parameters such as power and energy. These are very important. I think you people can understand or tell perfectly than me. ऐसा लगता है मुझे. It's okay. So if you see the graph, okay, if you see the graph, there is a capacitor, you can say, at the left side, or fuel cell, you can say the fuel cells are present at the downside but at right side. Okay, so fuel cells device, so all these are devices actually. So fuel cells energy, specific energy, per gram per kilogram is very high when compared to the other devices. But when you go to the battery, in case of battery, the energy is bit less, but power is comparatively high when compared to fuel cell. So when you again shift to electrochemical capacitor, so I will come to the supercapacitor and battery later. But in case of supercapacitor, the power is very high. See, the electrochemical capacitor, which are also called as supercapacitor or ultra capacitor, the power is very high. Energy is going to decrease. Again, in case of capacitor, which is the metallic type of, I mean, pure metals are used in capacitors. So power is again very high, but energy is less. So this comparative plot is called as Regone plot. And what is the thing it is related to Regone plot is that each and every energy storage related paper, I'm sorry, the authors have to show this plot in their particular data. What this plot stands for? This plot stands for the deliverable of that particular energy storage cell or device. So what research people are doing in the laboratory, they are just making a small device in the laboratory, not the actual which is done in the industry. But we have an idea of energy and power value of our electrode material prepared for that particular energy storage device, and we'll calculate the specific power, specific energy, and we put in x and y axis plot, and we'll get the data, and which is called as Regone plot. So what we understand with this Regone plot is that whatever the device the people are working, whether they are working for fuel cell, battery, lithium ion batteries, or any kind of other battery, zinc battery, sodium battery, magnesium battery, many kinds of batteries are there depending on the availability, we can say. And supercapacitor, capacitor, what I am trying to tell all of you, these parameters, specific energy as well as specific power, the specific energy is nothing but the energy stored in that material per unit gram, and specific power is nothing but the power stored, or sorry, power generated per unit gram. So what we can say, these parameters, these deciding parameters of the device, specific energy as well as specific power, should be as high as possible for any kind of device. Okay, so for fuel cell it is very difficult to increase the power, because they are already on the high energy side. So people are doing research to increase their power. For example, supercapacitor, their power is good but energy is less, so people are working to increase their energy, like that. So of course any device research is going, I mean many device energy research is going on, I'm sorry. But the thing is that the device, energy storage device, should be safety, and the safety issues are there for any kind of these devices. So safety should be the first priority, and the cycle life should be very high. Means like lithium ion battery, we have purchased a new mobile, but its battery is not working, say let's say within 15 days it is not working, so it is not good. So the cycle life, the life of that particular energy storage device, whether it is lithium ion battery, fuel cell, electrochemical capacitor or capacitor, it should be longer cycle life. And of course the end thing is the cost. So we are doing so many things, we are getting high energy, high power, but the cost is very high. What is the use of that? So the energy parameter, the power parameter, and the safety and cycle should be as high as possible, but the cost should be as less as possible. And this kind of things are going on in the field of these energy storage devices, and that is why this is the comparative plot, we can say. It is called as Regone plot. Okay, so let me shift to the next slide. So research on energy storage devices. So many students ask me whenever I tell that, yeah, this paper is now published and this is happening with us, and whenever I go outside or any friends we meet, so they say, what kind of thing you are doing, what is the meaning of research of so each and every area has different meaning. For as far as energy storage devices are considered, so what is the energy storage research is there in case of energy storage devices? What is the research? So the first is cathode. Whenever you see a battery, there are two ends, positive terminal and negative terminal. So people are making people are I mean discovering or synthesizing new cathode materials, new metal oxide based, carbon based materials for their application. then we can synthesize, or we can have original new anode. Okay, and people are also searching for new electrolytes. So electrolyte, if you focus on water based electrolyte, it has a voltage limitation, and because of that the energy stored per unit gram is very less. So if you talk about organic electrolytes, its voltage is more than 3 volt. So energy is directly proportional to square of the voltage, and because of that people are trying to increase the energy by discovering new kind of electrolytes. Again, there are many issues that some cathode are not capable to fit with the particular kind of electrolytes. Some anodes have some problem with that particular electrolytes. So these things are going on. So these three things have to come together to have a better research publication. So if somebody asks what is the research in energy storage devices, so people are either developing cathode, new anode, or the existing cathode with different morphology, different properties like that, and new completely electrolyte. So these three things are going in the field of energy storage. And if somebody is working perfectly in any one of the problems of this, he or she will definitely going to get a good quality publication or high impact publication. So research on energy storage device, this is going on, nothing else. So if you have an idea of a cathode, if you don't know about anode, that is fine, you can collaborate with people and say that, sir, I have a new idea about this cathode, I have a new idea about this anode, or I have an idea about electrolyte. So if you talk about electrolyte, so organic chemistry people are good in making electrolytes because organic molecules are there. Like engineer people don't know how to synthesize certain organic compound, how to make cathodes and anode, how to modify surface, but engineer people can make perfect device, that I know. So it is a kind of thing that we all have to come together and do a research on many things. But as far as these energy storage devices are considered, definitely all people are going to engage in such a kind of research, I can say. So going to the next slide. So I'm coming to the supercapacitor. So supercapacitor, wait a minute. Yes. So supercapacitor, okay, it is divided into first as electric double layer capacitor. Please remember, in case of electric double layer capacitor, it is a symmetric supercapacitor. It means that cathode and anode are going to be same. So I told you what is energy storage research. Any device, you can take supercapacitor, lithium ion battery, it has two electrodes. So both the electrodes are same in case of supercapacitor, and if they are carbon based, it is called as electric double layer capacitor. In case of pseudocapacitor is like bulk storage, like metal oxide. So here I have written metal oxides or conducting polymer. So what is happening with pseudocapacitor? Again, the two reactions in the chemistry, that is oxidation and reduction. So charge is stored in case of supercapacitor by means of oxidation and reduction reaction, that is redox reaction. Okay, and again hybrid capacitor concept is also there. Okay, in which at one side metal oxide is there and at another side carbon based material is there. So right side has a different mechanism of charge storage, and carbon, it has a different mechanism of charge storage. So I have written here electrical double layer electric double layer capacitor. It exclusively made up of similar type of carbon, and both the electrodes are same. And their mechanism of charge storage is like that: on the surface of the electrode, if positive charge is there, if positive terminal is connected, negative ions, I mean anions, are coming there, and there is a force of attraction between the positively charged electrode and negatively charged anion. Similarly, on the other hand, the same electrode is there but negative charge is there. So cations are getting attracted there, and there is a charge storage taking place. I mean, just a force of attraction. This is called as surface adsorption. So in case of electric double layer, only surface is involved, and because of that, okay, because of that, the energy is less. Okay, but the distance is reduced drastically. It is in nanometer, and because of that, power is more. Like that, concepts are there. So whatever the double layer capacitors are there, okay, they are based on the carbon based electrode, and at both the side the same electrode is there. And in case of pseudo capacitor, okay, the working electrode undergoes oxidation and reduction. Okay, so what kind of, so these two electrodes should not touch to each other, so there is a separator between them, and the separator is doing a job that two electrodes should not short. Okay, that is the job of the separator. And during the when we do this assembly, there we can pour the aqueous electrolyte like KOH, 1 molar KOH, 0.5 molar H2SO4. And if you go for the non-aqueous electrolyte, like I told you, organic electrolyte, their voltage window is, yeah, their voltage window is 0 to 3 volt. Okay, so I told you, if the voltage window is more, then the energy density is very high. Okay, and that is why the commercial supercapacitors are non-aqueous based supercapacitors. But thing is that in many laboratories, in many even college level people, they do their measurements in aqueous electrolyte because of non-availability of facilities like non-aqueous electrolyte. Because these kind of supercapacitors we have to construct in the inside the glow box, which is very expensive again. So you can initially start your research in your laboratory by taking aqueous based electrolytes, and we can apply those concepts to non-aqueous like that. So there are many papers again people are publishing in aqueous based electrolyte. Even I have published many papers in aqueous based electrolytes because of facility limitations. Okay, so what is principle of electrolyte? I told you. Okay, this is negative side and positive ions are coming and there is just adsorption. And here at positive side negative ions are coming. Okay, and there is a just adsorption. So EDLC means electric double layer capacitor store charges at electrodes. Okay, wait a minute. Yes, store charges at electrode electrolyte interface, okay, by forming double layer, and that is why it is called as double layer capacitor. Okay, for example, I told you, in case of electrochemical double layer, we are going to use activated carbon, graphene, CNT based materials. So activated carbon, graphene, CNTs I will discuss briefly in the coming slides, but they all these three are the forms of carbon. Then pseudo capacitor, many metal oxide hydroxides you can take, but if you focus on this is nickel hydroxide. Okay, so nickel hydroxide has lost the electron. So from left to right, it is oxidation. And when you come back, okay, there is acceptance of electrons. So pseudocapacitor based electrode store charges through reversible Faradic reaction. So in case of pseudocapacitor, there is Faradic mechanism. And in case of electrochemical double layer capacitor, there is just adsorption, desorption. So whenever there is adsorption and desorption, no complete involvement of electron material is taking place in the reaction, just adsorption and desorption. However, in case of pseudocapacitor, there is complete involvement of a material. It undergoes oxidation and it undergoes reversible acceptance of electrons. Are you getting the point? So whether it is nickel hydroxide, ruthenium oxide, MnO2, these are famous examples that is why I have taken. So what is the principle of supercapacitor? I can say that in case of double layer, there is adsorption and desorption. And in case of pseudocapacitor, there is a Faradic mechanism like oxidation and reduction. I hope the point is clear. Again, coming to the applications, supercapacitors are required where the high power is generated, like crane, when we want to start aeroplane, or high power UPS, we can say. So in very short time, if you require very high power, at that time, supercapacitors are important. So coming to the lithium ion battery, okay, so just forget about this complicated reaction. What I am trying to tell all of you again, in case of lithium ion battery, charging and discharging like our mobile, because there is a lithium ion battery inside our mobile. Okay, previously we were about to remove our battery, but nowadays it is fixed. We cannot remove our battery from our mobile. I mean, we have to go to the repair shop and get the things done. Still few people can, few people are smart, they can do that simple job as well. Okay, but what is lithium ion battery? So I told you, there is one cathode and there is one anode, that is it. And in between these cathode and anode, there is a separator and electrolyte, organic electrolyte is there. So during the charging, what is happening? Lithium is going into the solution and leaving its electron. So we can say that lithium is going to oxidize. And in the reverse case, okay, lithium is again coming back to the cathode and accepting one electron. There is a reduction of lithium plus, we can say. So if you want to understand the in terms of anode, see, so anode is generally graphite. It has a interlayer spacing, like I told you, AB type structure. So in between those layers, lithium can percolate. Lithium is coming, okay, from cathode, we can say. So carbon has a space, carbon layers, like 52 cards. Okay, I told you about 52 cards. So there is a space, and lithium can easily go inside that particular carbon interlayers with electrons. So there is a reduction taking place inside the carbon of Li plus. So sorry, during the charging, and during the discharging again Li plus is coming. This is the discharging and this is the charging. So what I'm trying to tell here is that principle of lithium ion battery similar to principle of supercapacitor. I am trying to discuss the principle of lithium ion battery. So you can see here lithium is coming here and again coming back here. So lithium is going forward side and backward side during charging and discharging, we can say. So this cathode is lithium cobalt oxide. You can see this is lithium cobalt oxide. Cobalt oxide is there, but it is lithiated. It is lithiated, and anode is a graphite. So I have purposefully taken this image because it contains metal oxide at right side. Okay, this is the structure of that particular metal oxide. It has a layered structure, and lithium is coming and going inside here, and graphite is also having layered structure, and that is why people are using graphite, because it has a layered structure. It is conductive and it can accommodate Li plus easily, because this distance also going to support the this distance is going to support the lithium size as well. So back and forward side or back and forth lithium ion is coming and going, coming and going, and because of that we can say the charge is going to store. So what is the electrolyte? It is 1 molar LiPF6. Okay, this is anionic part, this is cationic part, and this inorganic complex, okay, it is dissolved in organic solvent like ethylene carbonate and diethylene carbonate. So these are volatile electrolytes. So we cannot construct the lithium ion cell outside. We have to construct this lithium ion cell inside the glow box. Please remember this. Okay, so all these batteries and supercapacitors, they are applications of electrochemistry. So what is electrochemistry? We know that electro means electron and chemistry means chemical reaction. So interconversion of electrical energy and chemical energy is nothing but the electrochemistry. So there are two types of cells: electrochemical cell and electrolytic cell. So in electrolytic cell, the case is different. Electric energy is converted into chemical energy. But in case of supercapacitor and lithium ion battery, which are examples of electrochemical cell, in which chemical energy is converted because of chemical reaction, we are getting electricity. So lithium is getting oxidized and leaving behind electron. So we are producing electrons. That is it. That is the basic principle of lithium ion battery. So what are the scopes? What are the opportunities here? We can develop cathode. Okay, we can change its morphology, we can change its size, we can bring another layered oxide material which may have the higher energy density or say power density when compared with lithium cobalt oxide, or we can use different kind of lithiated metal oxide. That is the opportunity present for a researcher. Again, in case of anode, graphite is there. Now in commercial battery, lithium cobalt oxide and graphite are present there. So people are working to replace graphite by graphene or say another interesting carbon based nanostructure. But thing is that if we have cheaper graphite, okay, then why to go to another allotrope of carbon which may or may not be stable? Still people are searching for that. And if we are getting higher value of charge storage, then definitely in coming days we'll see another carbon present in the lithium ion battery device. Okay, so let me come to the very important point that lithium battery is a bulk storage. Battery is a bulk storage. So battery is a bulk storage. What does it mean? There is one cathode and there is one anode. Okay, both should be same size. Please try to understand. And this is a separator, and there is a electrolyte. There is a electrolyte between this device, we can say. So what is happening in battery? There is complete oxidation and reduction. There is complete oxidation and reduction. So what I can say, the complete material is going to involve in case of battery. Complete. So it is a bulk phenomena. It is related to bulk storage. It is related to bulk storage. However, whatever the electric double layer capacitors are there, if it is positively charged, okay, and if there is one more electrode, okay, and it is negatively charged, let us say, so positive ions are attracted here. Sorry, negative ions are attracted here and positive ions are attracted here. So this is just charge storage at surface. Charge is getting stored at surface. So what I can say here is that just the difference is that the distance is nanometer. This distance is in the nanometer, but this distance here is, there is no question of distance. The complete bulk of a material is taking part in the whole material is going to oxidize and reduce, and because of that we can say that yeah, battery is a bulk storage phenomena, whereas yes, supercapacitor is a, it is surface storage phenomena, we can say that. So how these properties are measured actually, electrochemical tools are required to measure the supercapacitor and lithium ion battery properties. So what we do in case of lithium ion battery or a supercapacitor, we have to record a cyclic voltammetry. That is a plot, it is for at constant voltage how much current your device is getting. I'm sorry, how much current your device is producing. So this is particular instrument, auto lab, and this is used for this is used for cyclic voltammetry, and this is used for charge and discharge study, and this is called as Solatron electrochemical workstation. So what you have to do before put that particular cell to for the measurement or electrochemical analysis, we have to fabricate that cell in the glow box. So first current collector is there. On that current collector, our first anode is there. Then separator, polymer separator is there. Then you have to drop cast the electrolyte. You have to fill that. It's not more than 5 rupees coin. Okay, just lab level I am telling you, because industry level it is very difficult for me to discuss here. What I am doing in the laboratory, that I am trying to tell all of you. I'm sorry. Wait a minute, sir. Okay, so this charge discharge instrument, okay, uh, so we have to apply a constant current and see the behavior of charging and discharging. So generally people are calculating calculating the specific capacitance or energy storage based on the discharge time, how much time it is taking for discharge. So more is the time for charging and discharging, more will be the capacitance. That is the simple thing, and we need to remember that. So this particular instrument used to measure the, I mean, this is one cycle at 1 ampere per gram. We may put 10,000 cycles. So 10,000 times it will go upside, and 10,000 times the particular cell come again to the, I mean, from 0 to 1 volt and 1 to 0 volt in case of aqueous electrolyte. And in case of organic electrolyte, it go from 0 volt to 3 volt and again come back from 3 volt to 0 volt. So we have to repeat this cycle, and we have to make a statement that its cycle life is good. So if it is going for 10,000 cycle, it means that our material is performing well, and it is very tough for the charge and discharge kind of study. So like that, few measurements are there. I'm not going in the details of that. Again, the thing is that this is the theoretical capacity, some calculations are there. I'm going to skip this. So this material is very important, which is present in commercial batteries, I told you. So it has layered structure like cards. So lithium can go inside after oxidation, and electrons coming from external circuit, and lithium plus get reduced and get stored there. Again, in the reverse cycle, Li plus again coming back. Okay, again electron going from outside, and there is a again in at that side of electrode there is a lithium storage is happening. So electricity we are going to produce by means of chemical reaction. That is why it is an example of electrochemical cell. So lithium ion is loosely held with oxygen than cobalt, hence easily de-intercalated. So that particular process of insertion and de-insertion is called as intercalation and de-intercalation. So what are the challenges of lithium ion battery? So we all know about these smaller batteries like our mobile battery, laptop battery. So these are like smaller applications, we can say. So if you go for electric scooter, if you go for the car, the size of battery is going to increase. So we can say that if these are the A applications, Okay. B application is 100 times larger when compared with A. And if you go for renewable energy, it is 1,000 times bigger than or larger than B, we can say. So safety is a major issue, we can say. If size of battery is increasing, we know the risk is I mean, risk levels are very high. Oh, when the battery is going to explode, we don't know. We are not sure about that. Although people are taking care, safety, so many things are there, but we cannot neglect the safety issue of lithium-ion battery. Although technology is going to develop. Okay, so these are the properties of nanomaterials. Okay, I will not. I'm not going into the details of properties of nanomaterial because we all learned this in our previous lecture. Just I will brush up the things. So optical properties, I told you, gold is depending on size, gold has different color. Okay, again the at bulk level materials are nanoparticles, show are opaque, but at nanoscale they are transparent. We know all these things because of a modification of the electronic levels and nanoparticles. With the help of size, we can comment that below particles having less than 20 nanometer size are good in are going to show absorption phenomena, and more than 100 nanometer, of course these are not nanoparticles, they show scattering phenomena. Then the electrical properties, we know in case of ceramics, electrical conductivity is going to increase as particle size is going to, but in case of metals, okay, the electrical conductivity is going to decrease with decrease in size. Okay, then of course mechanical properties are going to increase as particle size is going to decrease. So as far as mechanical properties are concerned, we know strength, hardness, toughness, ductility, rigidity, etc. are going to increase. Similarly, if you talk about the certain kind of cements, so people may use the addition, may prefer to add nano tin instead of adding nano Al2O3, because it is going to give a I mean the amount of which should be added and in what quantity should be the added. Okay, that is playing an important role, we can say. So mechanical properties also depend on which kind of material you are going to add or going to mix, and what, in what percentage, what is the ratio. These things are very important. And again magnetic properties, yeah, this is not my area actually, but still I have taken to cover the things what are happening with the help of nano, that magnetic nanoparticles can display super magnetic properties. So it may increase by adding an external magnet. Then nanomaterials are more magnetic than bulk materials. Okay, this is important. Even non-magnetic solids become magnetic when reduced to nanoscale. So examples are there: sodium and potassium behaves as paramagnetic at bulk, but they are ferromagnetic in the nanoscale. So FeCONI shows ferromagnetic behavior at bulk, whereas supermagnetic at the nano size. Okay. And then chemical properties, I told you in the previous lecture as well. So melting point, as size decreases, size increases, sorry, as size decreases, temperature is also going to decrease, but surface area is very high. And as surface area is very high, okay, nanoparticles are highly reactive. That, yeah, it is there. So this I already explained that how surface area is going to increase in case of nanomaterials. So nanomaterials are more reactive than bulk materials because of high surface area, we can say. So when we break the bond to make a nano size, it gets high surface energy. Okay, so the thing here written is nanomaterials are extensively unstable. What does it mean? It means that they want to immediately react with the things present in the inside the reaction media. If they are if nothing is present to react, they try to agglomerate. So nanomaterials are extensively unstable. They immediately come together and again produce a bulk material, or not nanomaterial, we can say. So whatever the reactions are there, nanomaterials are extensively unstable, we can say, but after some time their reactivity decreases because of agglomeration, we can say. Again, this size effect I already discussed. Okay, band gap is going to increase if the, I mean, electronic levels are going to modify as we talk about the size effect of nanomaterials. Okay, so next thing is that very important thing that I told, that I will be speaking more specifically today on energy storage, not on the more details of like general things, but I will be speaking on energy storage. Firstly, I will introduce about carbon, and then we'll go with the things that are present. in the carbon and its publication, that I did the work in the field of carbon, I want to say. So earlier, I mean, during 1800 to 1900, carbon materials were first used in batteries. Okay, then in 1900, carbon rods become a key component. I discussed just now. Dry batteries, then emergent of activated carbon. So activated carbon is something which is having high surface area. Okay, like if you compare activated carbon with CNT surface area is very less, like 10 meters square per gram. But if you talk about activated carbon, its surface area is always more than 2000 meters square per gram, like that. So surface area is very high in case of activated carbon, and people use that particular activated carbon in the field of supercapacitor. I told you, electric double layer supercapacitor. Electric double layer capacitor at both the side, cathode and anode, made up of same material, same carbon material. Here also activated carbon, here also activated carbon, like that. And then graphite and lithium ion batteries, I told you how graphite structure is helpful for lithium intercalation and de-intercalation. So graphite based lithium ion batteries utilization, invention during 1970s and 1990. Then activated carbon in supercapacitor, actual I told here as well, but yeah, it is also there. I mean, in 1990s. Then activated carbon-based materials, that also people also activated carbon nanotubes. Then graphene, it was first isolated in the year 2004 with the help of Scotch tape that we learned in our previous lecture. And then dope carbon materials like nitrogen, sulfur, these are heteroatoms. Okay, there are many kind of dopants because they enhance conducting properties. So I told you that carbon show just double layer phenomena, but by doping nitrogen, sulfur, it has pseudo capacitive enhancement as well. So it is kind of hybrid thing. Okay, it's like dope carbon atom. So during 2000 2010 that has started. And then porous carbon, hierarchically porous, means porosity is not fixed, it's not of same size. There are different size porosities present. So more research started during 2010 and 2020. Say carbon composite, I mean, like metal oxide is not stable, or it's not that conducting. So we have to coat metal oxide on the surface of the, or we have to make a composite with conducting carbon. So whatever the electron hole pairs are generated on that particular metal oxides, that electron is captured by that conducting carbon, conducting support, we can say. So it has better properties when compared to only transition metal oxide. So the carbon composite came in picture during that time, and people are now also working on hybrid materials. Then these are the things that is happening with carbon. I'm not going in the details. Of course, synthesis methods of carbon are there. There are many methods like pyrolysis of organic precursors, that I will tell you what is happening with this chemical vapor deposition. People are using acetylene, methane, and at high temperature they are producing CNT and graphene. So graphene, if you talk about Scotch tape graphene, it is very useful. Its properties are very very excellent properties if you talk about single layer Scotch tape graphene. But when you talk about chemically prepared graphene, its properties are decreased. But the thing is that in case of chemical method we are getting graphene in bulk quantity, but in case of Scotch tape method we are getting just single layer. What is the use of that? So we want properties of single layer graphene by chemically. Okay, by chemical synthesis people are working in that area. Then sol gel method. Okay, organic and inorganic moieties are there, and they are converted to gel, and followed by pyrolysis. People are using templates kind of things, and they are preparing carbon. And then template assisted synthesis there. So if you have carbon, like let us assume that a tennis ball, okay, and let us assume that a football. So on a football you can see hexagons, and you on a as well as pentagons. Pentagons are there, like they are pentagonal hole, hexagonal holes are there. So people are achieving creating a whole structure, perforated structure in carbon structure, whether it is zero dimensional, one dimensional, two dimensional. That is not a question, but in incorporation of holes improve the surface properties, and hence the energy storage results. That is well known thing. So people are using silica templates, zeolite templates, like that, and these kind of stuffs to create a holy carbon, perforated carbon, we can say. and then the hydrothermal synthesis there. So this is kind of autoclave is there. This is stainless steel autoclave, but inside the stainless steel there is a Teflon flask is there, 100 ml, 50 ml, 75 ml, and we can synthesize the material at a very high pressure, because here you can see a screw, and people are tightening this by adding reactant materials and keeping that particular autoclave at 200 degrees Celsius. So at high pressure, okay, at high pressure the material is going to synthesize. So people are doing this kind of stuffs as well. So in addition to hydrothermal, there is also one more synthesis called solvothermal synthesis. So in case of solvothermal synthesis, of course, after hydrothermal or solvothermal synthesis, people have to pyrolyze that. I mean, graphitization takes place only at more than 700 or 800 degrees centigrade. But this is the initial stage. That pre-carbonization stage can be achieved by the way of hydrothermal synthesis and solvothermal synthesis. So solvothermal synthesis is the synthesis in which water is not used. It is completely water free, but like say ethylene glycol, triethylene glycol, water content is zero. So that particular synthesis methods are termed as solvothermal synthesis. Okay, so coming to the functional carbon. Okay, let me see. Yeah, we have time. Coming to the functional carbon, there is a diversity in the forms and functions, we can say. So we can see carbon. It is a Fullerene zero dimensional, one dimensional carbon nanotube. This is single wall. This is multi wall. This is diamond. Completely different properties. Non-conducting. Graphite, it is conducting. Graphene is highly conducting, high surface area. So these are the many properties are present in carbon. That is why carbon is called as functional material. So carbon is sp2 hybridized, carbon is sp3 hybridized, dimensionality is there, conductivity is varying amongst the allotropes of carbon, surface area is varying. In case of single layer graphene, it is 2600 meter square per gram, but in case of graphite, it is like 50 or 60 meter square per gram. Then conductivity is very high. Both graphite's conductivity is also high, graphene is also high, but single layer graphene is again high. So inertness, reactivity, porosity. So we can play the structure of graphene with porosity, okay, but we cannot play the porosity kind of thing with graphite. So there is a scope, we can say. There is a diversity in the form of carbon, and because of that, we can say there are many opportunities as far as we want to develop a good supercapacitor or carbon-based supercapacitor or lithium-ion battery electrode. So let me come to the point, that is graphene. So graphene's research is going on worldwide. Okay, so what is the actual structure of graphene? It is a HRTM image, high resolution transmission electron micrograph of graphene. You can see the distance, and you can see the clear cut hexagon. Okay, like it is called as honeycomb lattice. So single layer graphene is just observed in squash tape method, and whatever the chemically prepared graphene is there, it has 50 or 60 or up to 100 layers stacked on each other because of van der Waals force of attraction. So graphene is the allotrope of carbon, but it is one atom thick, we can say. It is a carbon-based nanomaterial. So what are the carbon challenges? Let me come to the point and what we did in the field of carbon that I am going to tell you now. So the first thing is that surface area. So although I have mentioned many times that the surface area of graphene, theoretical surface area is around 2600 meter square per gram. But when you prepare graphene chemically, okay, squash tape, we cannot maximize its yield. Even it is very difficult to get 1 gram from squash tape method. Okay, but from chemical method, we can produce in kilograms. But the problem is once you prepare chemically, all the carbon sheets are going to agglomerate with each other. So reducing the surface area. We know if the layers are separated, then the surface area is high. But if they are coming together by van der Waals force of attraction, what is going to happen? They are reducing surface area. So the challenge is how to improve the surface area of chemically prepared graphene. That is the first point. So we have undertaken this and we have increased surface area of graphene chemically. How? I will show you in the next slide. The next thing is that pore volume. How to increase a pore volume? Pore is there, but it has no volume. So how electrolyte ion is going to, I mean, how cation and ion percolate or go inside that pore, and how the charge is stored. So in order to have more charge storage, pore volume should be high. So this is one of the area that people should work if they are working in the field of carbon. Then conductivity. So if you talk about chemically prepared graphene, in case of graphene preparation, we have to introduce oxygen first, which is called as oxidation of graphite. And once we get graphite oxide, we have to remove that oxygen, and we have to then we'll get only graphene. But thing is that chemically it is not possible to remove all the oxygen. So once the oxygen is inserted inside the graphite layered structure, in case of graphite oxide, it loses its conductivity. But after reduction, again it regains the conductivity. But thing is that all the oxygen containing groups are completely not completely removed, and because of that, the emerged graphene is not that conductive. So people have to find out the new reducing agent, okay, in order to get a good conductivity of that particular graphene. Then sp2 carbon content, this is also important thing. So in one of the review articles, it was written there that whatever people are preparing graphene, their sp2 carbon content is very less, and because of that it is less conductive, or it is not performing good in so and so applications, in supercapacitor applications, in another kind of application. So what people are trying, I mean, I personally try to increase the sp2 content of graphene in one of my research articles that I'm going to share with you right now. Then the yield should be as high as possible. Again, if we are not going to produce in gram scale or several kilogram scale of that particular graphene with good properties, then what is the use of that method? So yield should be as high as possible again. And the last thing, that is that the method should be green. So if you are using too many chemicals, if you are doing if you are preparing graphene but you are wasting too many chemicals, and you are harming the environment, what is the use of that? So these are the challenges in the field of carbon that I personally felt, and that is why I have written here. And I have worked on all these challenges and published papers. So these are actually the challenges that I withdraw from the review articles, and then I worked on each and every problem and I got a paper. So let's yeah, we focus on all the challenges and published papers. So this is the first paper that is accepted in Journal of Material Chemistry. What we did, we just replaced the hydrazine hydrate. People were using hydrazine hydrate for reduction of graphite oxide. I told you, here is a graphite, here is a graphite, and graphite is oxidized first to graphite oxide with the help of KMnO4. And here you can see the downside approach is a toxic approach, where people used hydrazine hydrate in order to get graphene. So what is the difference between graphite oxide and graphene? You can see red color here. These are oxygen containing functional groups are there. These are oxygen. So after reduction, oxygen is removed. So what I produced graphene by using triethylene glycol, which I named it as trigol reduced graphene. And conventional method, people were using hydrazine, and that is why it is called as hydrazine reduced graphene. So you can say we have just given a message that we are not going to use. What was the motivation behind that work? Behind that work, the motivation was like that. We used a polyol, which not only act as a reaction medium, but also play the role of reducing agent. So this trigol reduced graphite oxide into graphene, and again it is not toxic. It is not that toxic. So you can see the supercapacitor performance. This red one is for hydrazine reduced one, and this black one is for trigol reduced one. That is the reducing agent we used. I hope you are getting the point. And graphite oxide is a insulator. It is not showing any charge storage performance. So this is the first work, okay, which is nothing but the trigol based reduction of graphite oxide to graphene for enhanced charge storage activity. So this trigol is just simple replacement, and this is the first challenge, okay, green synthesis, and that we use, and we got a paper of this. And this is the mechanism. I'm not going into the details. You can see the carbon sheet is there, oxygen containing functionalities are there. One of the functional group epoxide I have taken here, and the trigol may attack like that. So we have predicted the mechanism, and finally you can see this is the graphene in which oxygen is absent. So in graphene, oxygen should be absent. That is the requirement. Okay, that is the requirement. And this is charge storage. You can see trigol based graphene delivered 125 farad per gram capacitance, specific capacitance, compared to hydrogen reduced graphene, and this geo is not showing at all any capacitance. So these are the charge storage performance or electrochemical properties, we can say. I'm not going in the details. So what I want to highlight is that, okay, our trigol reduced graphene at 1 ampere per gram applied current, where the material loading is 1 milligram, per centimeter square, we can say. It delivered a capacitance, specific capacitance of 130 farad per gram, whereas hydrogen reduced graphene delivered only 95. So these are the formula used to calculate capacitance and many charge storage performance by using that relation. This is the another work. So in which what we did, we have taken some plants, aquatic plants. We crushed into powder and we made a dispersion. This is crushed into powder, and this is we made a dispersion. We have filtered, and this is plant extract. So this is graphite oxide. This is brown in color. We have added this plant extract in graphite oxide, and we heated at 100 degrees Celsius, and we got graphene, and which is functionalized graphene, which is floating graphene. So it was challenging to make a functionalized graphene because graphene is hydrophobic. Okay, it settles down immediately. So getting a functionalized graphene, here you can see the in the title, functionalized graphene. So with the help of plant, so this is green, this is published in green chemistry. So we are using green, so green reducing, we have used green reducing agent. And you can see the graphene is a sheet like structure. This B is plant derived graphene, and this C is a hydrogen reduced graphene. You can understand CCG is chemically converted graphene, and this plant converted graphene, like that we have them. You can see here again the characteristics are matching with the chemically converted graphene. These are the images. This is the, yeah, this is, I think I have taken different image, I'm sorry. Let's go ahead. Yeah, this is the first slide work actually I have pasted here. So it's okay. This is trigon reduced graphene. You can see the sheet like structure, not that plant graphene. This is trigon reduced graphene. I'm sorry for that. And this is you can say this is hydrogen reduced graphene. So both are sheet like. So we are giving a message in the paper that we have given a message that we have prepared graphene by green method, and which has delivered a high capacitance. Again, the same trigon reduced graphene, we prepared a non-aqueous supercapacitor and lithium ion battery. And again, the results I told you how the lithium ion battery or non-aqueous supercapacitor is there. I will shortly explain here. This is the first current collector. Then you have to code that graphene, trigon reduced graphene on that particular current collector. And here blue color, there is a electrolyte and separator. Okay. And then again on the other side, there is graphene or lithium. When it is graphene, it is called symmetric supercapacitor. And when it is lithium metal, it is called as lithium ion half cell. So it is like that. This is a lithium ion battery, lithium ion cell, like small coin cell we can see in DMart. Like in digital balances, we have this kind of battery. Okay. And then this is supercapacitor. So in supercapacitor, both the electrodes are graphene. The cathode is trigon reduced graphene, and anode is also trigon reduced graphene. But in case of lithium ion battery, the one is a carbon based electrode, that is trigon reduced graphene, and another is lithium metal. And this paper we published in AIP Advances. That is fine. So I told you this is charge and this is discharge. Okay, this is potential window is 0 to 3 volt in case of organic electrolyte. I hope you are getting the point. Okay, and so this is supercapacitor. We are going to focus on discharge time. Longer is the discharge time, more is the capacitance. So of course the results are very less, but we used around 5 milligram of our active material. People generally use 1 milligram, 0.8 milligram for and show their result in the paper. But in this device, we use around 4 to 5 milligram sample, which is very high, and because of that resistance is increases, and as resistance increases, the charge storage capacity decreases. Still, these are the good results, I can say. And this is the Regone plot. I told you, you can see our material lies in this energy and power region. And then this is a lithium ion battery. So I told you at one side graphene is there, and at the other side lithium is there. So like that we have calculated lithium ion battery charge storage performance here as well. So I'm skipping this. So the next thing is that then another challenge is morphology modification. So graphene surface area is only 300 chemically prepared graphene, but theoretically Scotch tape derived graphene, theoretically it is expected that it should show 2600 meter square per gram surface area. So it is not possible to achieve chemically. 2600 meter square per gram. So what to do? See, here I have written the motivation is surface area issue for graphene. So why not morphological modification? So what we did, we prepared a graphene with holes. So you can see different holes, different size holes inside the graphene. So now this is positively charged, negatively charged ion coming sir, and getting adsorbed on the surface of positively charged graphene. And this is negatively charged graphene and positively charged ions are coming and getting adsorbed at the negative electrode. So this is the device we made by using perforated graphene, nano perforated graphene, and the perforation size was uncontrolled. So you can see 10 nanometer, you can see 50 nanometer, you can see 2 nanometer, you can see 10 nanometer. So why these holes are of different size? The questions asked at that time. So we concluded there that oxygen containing functionalities are present which are of different size, and because of that the hole produced is also of different size, and that is why we named it as a hierarchically nano perforated graphene is a good conducting good electrode or high performance electrode material for ultra capacitor or super capacitor. So this you can see this device has delivered around 350 farad per gram of capacitance, specific capacitance at to 2 ampere per gram, and this is the data up to 1000 cycle, and this is published in small. So the motivation or the challenge behind it was that the surface area of graphene was too less, so we cannot increase the surface area. Then what to do? So we have inserted holes in graphene, we have introduced perforations which are hierarchical, and because of perforations we got good results. So what is the key here? Just nano perforations. Okay, and how the perforation improved the properties you can see in this next slide. So how the process exactly takes place, I tried here with the help of TM images. This is the graphite oxide. Okay, so we have to mix with silica nanoparticle. So you can see on graphite oxide silica nanoparticles are assembling. Here is the bunch of silica nanoparticle, here few silica nanoparticles. So this graphite oxide has oxygen containing groups. So depending on the size of oxygen containing group, a bunch of silica is getting adsorbed there, chemically attached there. So after HF treatment, that silica is removed with the carbon attached to that particular silica in the form of carbon dioxide. And because of that, we are getting holes, we are getting perforations. So we claimed this first time, and because of that, we got very interesting paper. So this is graphite oxide. This is not reduced, but it is obtained with holes. And once you reduce with hydrogen hydrate, you are getting perforated graphene like this. So this is non-conducting D1, and this EH1 is conducting. So the downside is how we created perforations inside graphene, and upside is direct reduction. So graphene is there, but without perforation. So B is graphene only without perforations, but EH is graphene, but with perforations. And we called it as a hierarchically perforated graphene. So this interesting electrode material we prepared, and it performed very good in the field of supercapacitor. So why the hole is forming, explanation is here. So silica is when we add HF, silica is removed with carbon as carbon dioxide. So this is 11 standard test we have done here. So when a calcium hydroxide solution react with carbon dioxide, it produces white precipitate. So we concluded here that the carbon the carbon present in the form of oxygen which is attached to silica is removed in the form of carbon dioxide. We proved here. So whatever the carbon present here in geosilica hybrid, this geosilica hybrid, after HF treatment there is a evolution of carbon dioxide gas, you can see, and this carbon is coming from this graphite oxide. It means that it is creating a hole inside the carbon matrix, 2D carbon matrix or graphene matrix, we can say. So we have proved that, and our paper got accepted there. So you can see here different size images of perforated graphene. This is reducing scale, 1/5 the time, one half, then 1/2.5. So you can see scaling down, and you can see the hierarchical pores present in the graphene structure. So what is happening if the pores are there? So you can see here, this blue color line is for perforated graphene. See the performance. We reach about 500 farad per gram in case of perforated graphene. But this brown color is without perforation. it is even not reached to 200 farad per gram. But in case of perforated graphene, we reach about 500 per gram, farad per gram capacitance, specific capacitance. You can see discharge time for perforated graphene is very high, but that of only graphene without perforation is very less. Again, the charge storage performance, supercapacitor performance at 2 ampere per gram. Perforated graphene perform well. However, the non-perforated is only 130 or 140 farad per gram. So these are the, I told you, it's not possible to increase the surface area of graphene. See, our perforated graphene has only surface area of around 260 meters square per gram. And that of graphene, only chemically prepared graphene is around 400. Still perforated graphene is performing well because number of edge sites, number of holes are more. So catalytic sites are more. So electrolyte interactions are very high with perforated graphene when compared with the graphene which is not having any kind of holes or perforations. Okay, so you can see the porous morphology of perforated graphene where it is rough morphology in case of graphene without perforation. So this is a Regone plot. It's okay. So what I'm trying to tell all of you, we achieved a capacitance of around 500 in case of perforated graphene, but in case of non-perforated graphene, we achieved only 130 farad per gram. So one challenge we accepted and we did that. So another challenge, it is very difficult to prepare. So these three are battery materials. Fe3O4, I am coming to the oxide again. We have 15 minutes, I think. So I will rush the slides. So Fe3O4, TiO2 and SnO2, these are the oxide based materials. SnO2 stores the lithium ion by the mechanism of alloy formation. Like in 24 karat gold, there is some impurity. It forms alloy, and because of that, the gold is bit not soft. It is bit tough. Okay, because of alloy formation. So SnO2 react with lithium by alloy formation. However, TiO2, it has a layered structure. Lithium can go inside and come back. So intercalation and de-intercalation of lithium ion takes place in case of TiO2. And Fe3O2 is like oxidation reduction type of material is there. So all these three materials are different, but they want conducting support. So we have given a graphene support. Graphene prepared by green method, and we have prepared all these three materials by using single pot. In a single step, we have prepared, and same method we have produced three composite. And because of that, this paper has accepted in very good journal. So what we did, we have taken GO plus Fe precursor and heated at 280 degrees Celsius in trigon. In another experiment, we have taken GO titanium source and we got TiO2 graphene. In another experiment, we added tin precursor with GO and we got tin oxide graphene. So by using same method, we prepared three important lithium ion battery material. Okay, these are anode materials: Fe3O4 graphene, TiO2 graphene, SnO2 graphene. So I'm not going in the details, but I will show you. This is graphene sheet. Okay, and you can see Fe3O4 nanoparticles, monodisperse Fe3O4 nanoparticles are there, and how images we got there. Then this is the capacity we got around 900, around 7 to 800 milliampere hour per gram specific capacity in case of Fe3O4 graphene. So this is the tin oxide. You can see tin oxide particles are very, very tiny particles, around 1 or 2 nanometer particles. And you can see that all the particles are present on graphene layer only by the same method. So we have confirmed with X-ray diffraction, many things we confirm, and we have measured its capacitance, and see it is very specific capacity, very stable up to 35 cycles, and we got around 300 milliampere hour per gram capacity. And then this is TiO2 graphene. TiO2 not perform that well. There was some problem with the precursor, but the images are very good. All the TiO2 nanoparticles are covered on graphene sheet. So this we did only in single method we developed. Okay, and this is the bit lower result. People showed more than 200 capacity, but in our case the capacity was less, maybe because of some impurity. So the conclusion is that we successfully prepared three anode materials by single method, which are very excellent electrodes we prepared, and because of that it accepted in composite material science general. And we can say that this is green method, this is one pot method, and uniformly distributed smaller particles we decorated on graphene sheet, we can say. Okay, so this one I already discussed in the last seminar, last lecture, that we introduced perforation in spherical shape carbon, apple shape carbon, and because of in, but you can see that small paper is hierarchical perforation, but this is uniform uniform perforation. You can see, so that is why we said orderly meso perforated. So the holes are accurately 12 nanometer size, and that is why it is called as orderly meso-perforated spherical and apple-shaped 3D spherical and apple-shaped carbon microstructure. Okay, and then in the next work, I am just finishing. I'm a bit faster now. This one is one more method related to surface area. I told you surface area of carbon is also one of the challenges. So chemically, it is very difficult to prepare high surface area graphene. Okay, so we took a challenge. Okay, why the surface area of graphene? You can see many papers. The surface area is not even crossing 500 meter square per gram. So we started with the single molecule, single organic molecule, and with the help of silica nanoparticle, we clubbed all these organic molecules, and we heated those molecules. So we like stitching of small organic molecules chemically. We did that, and what is happened, because of graphitization at that 800 degrees Celsius followed by activation, we got excellent result. We got graphene like structure. You can see this is sheet like structure is there. Spongy graphene we prepared. How we prepared? You can see the result. This is a graphene like structure. One of the challenge I told you about the sp2 carbon content. So this is our benzene tetracarboxylic acid derived carbon. So we took some benzene related molecule, small molecule, we stitch chemically, okay, in order to get a graphene like structure, and whose sp2 content is very high, because benzene is sp2 hybridized material. It is aromatic material, okay, and sp2 content in benzene is very high, because all the carbons are sp2 hybridized. So that was one of the challenges I showed you in the previous slide. So how your graphene is going to reach in sp2 carbon content, that is also we undertook as a challenge. So we stitch benzene small benzene molecules together, and we increase the sp2 content here. So this is graphite. Actually it has 100% sp2 carbon, but in case of our carbon it is around 96%, around more than 96%. So more than 96% sp2 carbon we achieved here, and we activated that particular graphene, and we got the specific surface area of 2600. So both the challenges we achieved in our carbon related work. So you can see this is the carbon without activation. It is also 1000 meter square per gram. So this is bottom up approach. I mean, from small benzene molecule we got a graphene sheet like this, okay, and with a specific surface area of around 1000 meter square per gram. But in case of hydrogen reduced graphene, it is not even 500 or say 600. So we almost double specific surface area, and we activated this sample, and we got around 2600, sorry, 2675 meter square per gram of that much surface area we achieved. So what we can say in short, we have enhanced surface properties of this carbon. Okay, so that was the carbon based things that I did with carbon. Again, these things are going on, like morphology related issues, surface area, surface functionalization. These are the opportunities. People are discovering exins, 2D oxides, 2D nitrides. People are mimicking graphene structure in case of nitride, phosphides, borides, and exploring the application. I told you heteroatoms doping in porous carbon structure is also going on, because if you dope fluorine, it has some different advantage. Oxygen doping has different advantage. Boron, nitrogen doping. So all these kind of doping in carbon structure is going on. Then you can see, I told you, if you dope with silicon, it improves the structural stability. If you go with oxygen, it enhances surface polarity. Then if you go with phosphorus, it adjusts the change distribution, enhance ion adsorption capacity. So many things are improving. If you talk about nitrogen, it enhances electrical conductivity, and hence there is more just charge storage in case of graphene. So graphene, when you compare graphene charge storage and nitrogen dope graphene has more charge storage, like that. So doping has a perfect effect on the value of charge storages. Let me conclude with the metal oxides. Few slides are there. So the metal oxides, yeah, it is a compound of metal with oxygen. So like TiO2, zinc oxide. Then what are synthesis method? You can play with the temperature. You can change pH. You can change solvent. You can have solvent thermal, hydrothermal method, solvent free pyrolysis method, which is also a very interesting thing that I am doing. So if you are using solvent which is toxic, what is the use of that? People are saying use of water is important, but if we are not getting result in water, what to do? So we have taken a challenge to prepare metal oxide without solvent, and that to nanoparticles. People are using and people are preparing metal oxides without solvent, but that is solid state synthesis and particle size is very large in that case. So we have taken the challenge to prepare nanometal oxides without solvent, and that work is going on and we got excellent result, and we will get a couple of papers from solvent free synthesis of metal oxides and their applications in the field of energy or energy sector or diet degradation, like that environmental related applications are going on. Again, wet chemical methods are there. I'm not going to the details. Why metal oxides are so important? Because they have different crystal structures. Each and every metal oxide, because of their structure, has advantages because of their structure and useful for many applications. Simple oxides are there. I told you about calcium oxide, SiO2, Al2O3, nickel cobalt oxide, magnesium aluminum oxide. These are mixed oxide, perovskite based oxide, SrTiO3, LaFeO3, and then transition metal oxides, TiO2, Fe2O3, etc. There are many oxides. I have just taken their few examples, and these are the common nanometal oxides we can say. I'm not going into details. Let me come to the different processes present for the synthesis of the metal oxide. So Fe2O3, this is the electrospinning process. So by the with the help of this particular kind of assembly, we can produce a fiber like morphology of a material. So I told you fiber like morphology is important in the case of diffusion. Good diffusion processes like lithium ion diffuses very fast through this particular kind of structures, or electrolyte ions move get diffuses because there is a like pipe like arrangement is there. So the fiber like morphology is achieved with the help of this process. It's not related to Fe23. I have taken just only one example. You can prepare nano fiber morphology of anyone, any metal oxide you can prepare by using this particular tool, which is called electrospinning process. Then hydrothermal synthesis process, I told you Teflon and stainless steel is there. You have to mix these two precursors, and you can depending. So there are some orientation. What it is called? Yeah, some reactants you have to add. They have some plane growth in particular direction, and because of that, such things are happening. Like you are getting plate like morphology, you are getting flower like morphology, you are getting disc like morphology. This is again the case of Fe2O3 I have taken. So you can do with any kind of oxides, and based on that the applications are different. So this is chemical bath deposition. You have to take precursor and heat, and you will get you can convert that precursor into oxide. So you can also electrochemical deposition process are there. So you can take a substrate, and on the substrate you can deposit this kind of structure with the help of the electrochemistry. Okay, so you can go nano, you can grow nanotubes. This whole like you whole like structure you can see. So nanotubes you can grow with the help of such a electrochemical analysis. So again, this like structure, this is spindle shape structure you can generate for Fe2O3. So I have taken the example of Fe2O3 exclusively because I work Fe2O3. Fe2O3 is a wonder one material. Why it is wonder material, I'm going to discuss it in the next slide. And again, nickel cobalt oxide, various morphology people are preparing using chemical tools. Again, nickel foam is there, carbon cloth is there, carbon fiber paper. On nickel foam, people have grown nickel cobalt oxide. Okay, and yeah, these kind of things are happening in the case of oxide. So let me come to the paper which is recently published. So we have derived this BiVO4, Fe2O3 and carbon fiber, so ternary composite. So BiVO4 is there, Fe2O3 is also there, and this is grown on or carbon fiber support is also there by using MOF. Again, hydrothermal is involved here, and you can see here that I'm not going into the details. So we have degraded the methylene blue dye. So these are the result. No degradation of dye because we haven't added catalyst. So we have added our catalyst, this red color. BIFEC, and you can see here that within 120 minutes, over 99% of the dye is degraded. Okay, and here the tetracycline drug. This is also very dangerous because it contains chromium 6, which is hazardous. So chromium 6 is converted to chromium 3 with the help of our catalyst. This is BiVO4 Fe2O3 carbon fiber catalyst. So you can see tetracycline drug also lost his activity, dangerous activity, because it is converted from chromium 6 to chromium 3. Chromium 3 is not toxic. Chromium 6 is toxic. So you can understand in that way. So we see in 60 minutes we got around 90% degradation of tetracycline drug, and methylene blue is around 100% in 120 minutes. So these are the images of the material we prepared. With the help of HRTM analysis, we concluded that is Fe2O3 is also there, and BiVO4 is also there, and carbon fiber is also present there. Again, yeah, this I will skip. And metal oxides and carbon hybrid both have together more importance. I'm going to skip this. So this is carbon is going to enhance the properties of metal oxide. I told you conductivity of metal oxide is not that good, but with the help of conducting support we can have good properties. So because of that, people are interested in making hybrid materials like oxide and carbon together, like that. And then yeah, CO3O4 graphene, this is like yeah, अनार के शेप के जैसा ही बना दिया है. MNO porous carbon microstructure, and tested. Just see this synthesis. Okay, roles of carbon material: it is acting as supporting material, conducting co-catalyst, photocatalyst. Many things are there. So nanomaterials, okay, performance depends on, yeah, particle shape, particle size, many things I already discussed. Okay, applications, we know all these are the applications of metal oxides. Okay, and the biomedical applications are there, environmental related applications are there, that I am working in water purification, dye degradation. Many things I am working with oxide based materials, and I will show in couple of minutes our works with metal oxide. And I will stop just 2 or 3 minutes I will take, and I'm going to stop. So I told you in my last lecture also. So I am focusing on Fe2O3. So this is waste I have collected, and then I have prepared a chain like Fe2O3 for Fe2O3 nanoparticles. And with the help of TM analysis, we proved that it is Fe2O3 only. And you can see the lithium ion battery performance. This is for 200 cycle. Okay, the capacity is very high. The Coulombic efficiency of charge discharge is almost 100%. So the capacity is around, we got around 900 capacity, which is stable up to 60 cycle. Okay, so this kind of results we got. And then we also prepared BIO for, this is the paper just published in Energy Material, maybe 2 or 3 days back it is published. So what we prepared BIO for first time from MOF based synthesis is there. So these are the images. ABC is without carbon, and this is DEF is with carbon. So carbon is playing the role. So these are the devices we prepared. This is a symmetric supercapacitor in our laboratory. I will show you the video. This is charging and going on. Okay, and this is discharging at right side. And then we also prepared a aqueous based supercapacitor. This is charging at left side. This is yeah, discharging, and we got 160 farad per gram capacity. And the important point is that we use around 20 milligram of material, around 20 milligram of active material, and that is why the capacitance is bit low, but the device is very good. So you can see how we prepared a device. This is tic tac bottle, 5 रुपए का वो आता है ना टिक टैक का, तो टिक टैक सेल हमने बना दिया. टिक टैक, we have taken tic tac bottle, empty tic tac bottle. This is the stainless steel on which we have coated BiVO4 with carbon. C means carbon. BiVO4 with carbon content is there. The carbon content is very less. It's around 2 or 3%. Okay, and this is a separator. This is just tissue paper we kept over this, so that two electrodes should not short when we keep on one another. And then we have added the electrolyte, KOH based electrolyte, and we have prepared a device. So we have a device, you can see the video. Okay, this is two cells we have connected in series. This charging is going on. Yes, so after charging you can see the cell we made in tic tac bottle, 5 rupees tic tac bottle. We just accepted paper. So this is charging is going on. Okay, so once the cell is charged, we connect that fan. We are not that expert in device, but still we are trying. This charging is done, and now see, during the discharge the fan is operating. Okay, I hope the point is clear. And here we use the same electrode, that is BiVO4 with carbon, 2 or 3% carbon, and this is platinum wire. Okay, this is 3 electrode assembly, and we have generated hydrogen. You can see the hydrogen bubbles are coming. So this is hydrogen production. So OER application, same material. So these kind of advantages are there with our oxide based materials. And this is last paper, yeah, but yeah, the time is over, I know. Still this is a bit mechanism that light is coming, radicals are generating, and how the dyes are going. I mean, this at left side chromium 6 is converted into chromium 3, and right side you can see how this MB dye is going to convert into, it is producing carbon dioxide like that. It's completely degree. It is the bigger molecule is going to convert into the smaller molecule. So this is our catalyst, that is nickel cobalt. Sorry, yeah, nickel cobalt oxide and nickel oxide, which was the previous paper. I didn't explain. I mean, this paper I didn't explain, but this is the mechanism. So that is it for this talk, and yeah, this time I completely followed the time, and thank you so much for this opportunity and for your patience. I hope you got the point. Thank you so much.
Thank you very much, sir. Very informative session, very nice session, and your contribution in the field of supercapacitor and the work is very appreciating.
Thank you, sir.
So there are many appreciating words in the chat box also.
I haven't seen that chat box because
Thank you,
of
sir. Thank
presentation.
you. So anybody want to ask question? If any questions are there, you can ask. Very nice presentation.
Thank you, everybody.
Anyone is interested to ask any question? So very simple and maybe very small question.
Hello.
What is
Yes,
the
yes.
purpose of electrolyte in the lithium-ion battery?
Sir, electrolyte is a medium. Like means cation and anions are traveling through that medium.
Okay.
So that
And
is the,
separator?
because separatory is there, that the two metals should not connect to each other. If they connect, because if they once they connect to each other, it gets short.
And that's why
So
those explosions
yeah, no, no, no,
sometimes happens.
cell will not going to work if they connect to each other. I mean, we have to keep cathode and anode separate, and the separator is there. That separator allow that it is not directly in contact with two metals are not directly in contact with each other because of separator, because it is insulator. Separator is and
Yeah, yeah.
as it is insulator, but it has holes, so cation and ion can freely move from the holes. I mean,
Correct, correct.
separator holes, I mean.
So there are many times heard that the nowadays electric vehicles or even our mobile batteries get explode. So is there any
Yeah, there
reason
is, yeah,
of
there is,
this electrolyte
yeah,
or
yeah, yeah,
separator?
there, yeah, yeah, there is a reason of if you go on continuously charge and discharge the battery, actually we are charging mobile means we are charging our battery actually. So what is happening is the
Yes.
lithium cobalt oxide is there as a cathode material, and graphite is there as an anode material. So oxygen is there. Okay. So oxygen is there. So continuously during charging and discharging, what is happening? There may be evolution of oxygen gas. So if the space of electrolyte is taken by the gas, if the amount of gas is going to increase, then at some point there may be a chance of explosion.
Dr. Vinayak Kale is with us. Dr.
Okay,
Vinayak Kale.
Vinayak,
Uh,
Dr. Vinayak.
Thank you, sir.
yeah,
Thank
yeah,
you, Patil, sir. Thank you, Bajit sir.
Yes, sir. Please.
Hello, Dr. Dattakumar.
Yes, sir.
Very, very nice presentation, very informative. Congratulations for your recent updates and papers also.
Oh, thank you, sir. Thank you.
I have a very simple question. You work on both entities like carbon and non-carbon, I mean metal-based and non-metal-based systems.
Sorry.
So, is
I'm
what is your best suggestions? Which material should we choose for the exploration as an electrode for energy storage applications in general?
in general. Yeah,
Yes, sir.
in general, I mean, depends on device. If you are asking about supercapacitor, definitely we need to focus on graphene.
Okay.
And yeah, definitely, if you talk about, say, a lithium ion battery, we have to go with the more perfectly structured lithiated based oxide. Like cobalt is bit toxic, so we have to go with the eco-friendly or non-toxic metal oxides in case of lithium ion battery.
I see. I see. I got it.
Okay,
Thank you, sir.
thank you. Thank you.
Thank you, Vinayak, Dr. Vinayak. Tomorrow we will see you.
Okay.
Yes, sir. Yes.
Yes, yes. Anybody is having still any questions? Okay, so seems to be no questions, and everyone is appreciating your presentation, sir. Very informative, very nice presentation. Thank you very much on the
Thank
behalf
you, sir.
of Siddheshwar Women's Engineering College. Uh, Thank you for being with us and exploring your knowledge and your work. So thank you very much.
Thanks to
So
all participants as well. Thank you, sir.
Hello, sir. Hello,
yes,
sir.
sir. Yes.
Good evening, sir.
Hello. Hello.
Sir,
Please ask.
sir, one more thing, one doubt I have.
Okay.
Uh,
Go ahead.
in the PPTs, whatever the explanations has been explained, that is interesting part, sir. But
Okay.
what I was thinking, I'm using J-Octane Chimera software.
Which camera?
J-Octane Chimera software for material simulations.
Okay. Simulations.
For yes, yes, sir, yes, sir. Can we apply these whatever the applications you have explained? No, can I apply these applications in that one, sir, for simulations and analysis purpose?
Yeah, definitely. But that simulation is going to give you idea about the what kind of material you need, etc.
Exactly. Yes, sir. Correct, sir.
Yeah,
Correct, sir.
definitely. But for that purpose, you may need to prepare a series of compound synthesis,
Exactly correct, sir.
and you need to give the inputs, and that machine will give you what kind of properties and features will going to work in this particular thing.
Okay,
Definitely,
sir.
but
Okay.
thing is that everywhere, I mean, a person like me cannot use that facility. Like you people, I mean, a person like you have to help me in that case. So like
Yes,
that,
sir. Yes, sir.
yeah, it is
Because
theoretically it is very difficult. I mean, if you talk about Fe2O3, it is theoretical capacity is around 1000 milliampere hour per gram in case of lithium
okay,
ion.
sir.
But so what property should we incorporate? Like surface area should be enhanced, like some vacancies are there, some kind of doping is there. So how much percentage of doping, a series of experiment you have to give in that particular machine type of or software you are saying, like simulation. So it will definitely give an idea about that what up to level percentage you need to have a better result like that. Definitely it is going to work.
Okay, sir. Okay. Thank you so much, sir. Only this much I need to clear.
Yes,
And
100%
one more
is good.
thing, I need this PPT's video, sir, because the PPT was very interesting, sir.
Yeah, thank you.
Because
Dr. Avinash sir will give you. That is not an issue.
Yes,
yes,
yes.
sir. Yes, sir.
It will be
Even sir,
shared in
Avinash
the.
sir, that madam has also explained some related corrosions PPTs.
Yeah,
So
yeah, yeah.
that material also I want, sir.
So that PPT is already shared in the group.
Okay, and video. If I found videos, no link, I can download it and I can see whenever I will get.
Video I will. It will take time. The
Okay,
YouTube
okay, sir.
link
No
will be
issue, sir.
shared.
No issue.
It will be
Yes,
shared.
sir. Please, sir. Please, sir. At least if
All
you send the link, no, all
Yeah, yeah.
videos.
All sessions, all 13 sessions, video links will YouTube links will be there. In a one link only, all the sessions will be there as a playlist.
Yes, sir. Yes, sir. Okay, okay, sir. Okay,
You
thank you
can
so
see
much.
we
And
will add, but
till
PPT is already shared. PPT is already
yes, sir.
shared, and
Yes, sir. That I will.
I will
That I
share
will go
PPT
through.
of Dattakumar Mhamane sir also.
Okay, sir. Okay, okay. Yes,
Yes,
sir.
yes.
Thank you so much, sir.
So
Thank you,
thank
sir.
you all the participants. Yes, anyone is there asking question?
Uh, Sir, hello. Am I audible, sir?
Yes, sir.
Sir, I have a small doubt. Like the availability of the lithium on the planet is very less as compared to the
Yes,
sodium.
yes,
So,
yes.
is there any research going on the sodium side for the energy storage? And the energy density of the sodium is too low as compared to the lithium. So, is there any research going on increasing this efficiency of the sodium-based batteries? And is there any possibility in the future that we will see sodium batteries?
Yes, definitely. This is a good question. That the limitation of lithium, one of the limitations of lithium-ion battery is the its availability. Because similar to like how I talk about natural resources, similar to that, lithium is a, I mean, availability is big, but thing is that the size of lithium is very less. Okay, so people are yes, trying to develop sodium ion batteries as well, like in KPIT company Pune, there is one unit which is going on making e-scooter based on sodium ion battery. Yes, people are doing the job, people are inventing the sodium ion batteries. However, the capacity, as you said, is yes, less, but definitely it is very stable. Definitely it is very stable, and the size issues are there. So what carbon based material we are using for lithium ion battery may not be applicable for sodium ion battery. Again, the another kind of research is going on. So for sodium ion battery, hard carbon is more preferred than the activated or porous carbon. So this is a good question. Yes, definitely research is going on, but it's not to that level what lithium ion battery is reached. But definitely in future that will be the solution. So in my previous lecture, I have shown you that where can we go. So another option for lithium ion battery is the zinc ion battery and sodium ion battery, and people are going to do that. Is that clear?
Yes, sir. Yes, sir.
Okay.
Thank you. Thank you.
Yes. Let's wind up. Thank you once
Thank
again,
you. Thank you,
Dr.
sir.
Mhamane,
Thank you,
for
sir.
your valuable time
Yes.
and very nice time with you for two sessions, first day
Same here.
and today's fifth
Same
day.
here. Same
Okay.
here. Same here.
Yeah, sir. Thank you. Thank you very much.
Oh,
And
shall I?
for participants, I would like to again inform that tomorrow will be the last day, and we have a final assessment. Test will be at 6:30 to 7:30, 1 hour, and you have to give that test in your Atal login. In your Atal login. So don't miss